it's also pretty clear, since addition works coefficient by coefficient, meaning you just combine like terms, it's clear that if I add a to its negative, I will get the zero formal sum. Okay, also we have some rules of scaling, like scaling by 1 should leave the thing alone. That's very obvious because you just multiply every coefficient by 1. Also, if I scale by some integer m, and then scale the result by some other integer k, should be equivalent to a single scaling by the product k times m. And again, that's obvious, because the first time you do it, you just put an m into every coefficient, and then the next time you put a k into every coefficient. So it's equivalent to putting a k times m into every coefficient, kind of all at once. Right, and the last two are distributive laws, where a scalar, integer scalar, can be distributed over a sum of formal sums, and that's the one we just verified right here. And then the other distributive law is that you can have a sum of scalars and multiply that by a formal sum, and you get a correct distribution. And again, you can verify that the same exact way. So it's not difficult to check all the module axioms for the set of formal sums. And then knowing that the formal sums form a module, this type of argumentation here, where we just move all the operations inside the diamond brackets, that's the pattern here. Like the grouping that happens is moved inside the diamond brackets eventually, by first moving this plus sign inside the diamond brackets, and then moving this other plus sign inside the diamond brackets. Then it becomes a question of associativity at the level of formal sums, A, B, and C. No longer at the level of classes, but at the level of formal sums. And then using the fact that the formal sums form a module, we know the associativity there, so we can regroup, then just unwind all the definitions back again. And that same type of argument can be used to prove all of the module axioms for the chains. So every module axiom can be verified for chains as well. So yes, it is indeed still a module. Okay, so we now know that the chains over U form a Z module, meaning a module with integer scalars. Okay, and what I'm now going to do is I'm going to introduce another set of objects. So yeah, more properly, chains are called one-chains because they're one-dimensional. They're sort of composed of paths, formal sums of paths. And paths are one-dimensional objects. We can also define zero chains, which are basically formal sums of points. Points are zero-dimensional object. See, a path or curve is a one-dimensional object, sort of extended in one dimension, because you can move back and forth. You can move sort of back and forth along that curve. But a point is a zero-dimensional object. So if I have a formal sum of points, that's going to be called a zero chain. Okay, and actually the formal, so let me write it this way. I'll put a 0 as a subscript. And what I mean here is basically all formal sums. It's the set of all formal sums of points in U. The points have to be in U, that's why this U is written here. So I can't use points that are outside of U. But I can take any collection of points in U, any finite collection. Well, actually, yeah, formal sums means that only a finite number of the points get non-zero values. So actually, every point is assigned a value. Every single point of U is assigned a value, but most are assigned the value 0. And only a finite number of points will be assigned non-zero values. Okay, so you take all formal sums with, again, integer coefficients. And that's what I'm going to call the 0. Well, those are the formal sums. But I'll also call those zero chains, which I'll write this way. Okay, and then in order to distinguish the one chains, I'll also introduce this notation, C1 of U, for what I previously called C of U. For completeness, let's also introduce this notation, F1, for what I previously called F, just formal sums of paths. Okay, so these are formal sums of paths, piecewise smooth paths in U, and these are one chains in U, which again are just equivalence classes of paths under our equivalence relation. Right? And then C0 of U, which is just the same as F0 of U by definition, those will just be formal sums of points. Okay, why do they come out the same, whereas these two are not the same? Okay, the reason is because with paths, there were certain ways of combining them, geometric ways of combining them, that we wanted to take account of. For example, we had the ability to concatenate two linked paths to form a single new one. Right? Or we had the ability to reverse the direction of a path, consider its reversal. Or we had the ability to reparameterize the path. But you see, with points, there's no such options. If I have just a set of isolated points, each of which gets assigned some non-zero value, there's no geometric way to combine any of those. I can't link them together because they're not touching. I can't reverse their directions because they don't have directions. And I can't reparameterize them because they're already parameterized by like a constant function. And that's the only way that you can parameterize a single point. So, there's none of these geometric options. And therefore we just set these two notations to be equal to each other. Okay, so more specifically, what both of those sets are equal to is the set of all mappings Let me introduce some notation for them. Okay, notations are always difficult to have a different notation for every different concept. Okay, but like temporarily, let me call it like, I don't know, a Hebrew letter. Okay, I'll use the letter Aleph from the Hebrew alphabet. That's the first letter of the Hebrew alphabet. Okay, so like take Aleph. Like, see if I can even still write an Aleph. Which is, what is it? Okay, it's a map from the set of points of u, meaning just u itself, into the integers, such that Aleph of every point is 0 for all but finitely many. Like whenever p is not in some finite set of points in u. Okay? So basically every single point of u is assigned an integer value, but the vast majority of points are assigned the value 0. Only a certain finite number of points may be assigned non-zero values. So like Aleph of p1 might be non-zero. It still could be 0, but it doesn't have to be. This can just be any arbitrary integer, n1. Possibly 0, but not necessarily 0. Okay. Then Aleph of p2 is like n2, some integer. And Aleph of pn is n, capital N, some integer. But then Aleph of every other point is 0, if p is not any of those previous points. So that's what a formal sum is. And the same theory of formal sums works out here, where if I have two of these formal sums, let's say Aleph and bet, okay, bet is the second letter of the Hebrew alphabet, I can add the two just as functions. I just take Aleph of p and add that to bet of p. Okay? And again, when those are both 0, which is true for the vast majority of points, then the answer will be 0. So it's the same idea, where like you add them as functions, and you'll get something that's also still, like the sum of the two as functions is still in the same set, f naught of u. So it's f naught of u is closed under addition. F naught of u is certainly closed under addition. Okay, and we can also scale. It also makes sense to, so, and it's closed under scaling too. Scaling by integers, say m. So the way you would scale by an integer, like let's say I have some formal combination of points. Let's say I have like 3 particular points in my region. Here's my region U, and I've got these 3 specific points picked out that are all in that region. So this type of thing is a formal sum. So let's call it Aleph. Now how do I calculate, let's say, 5 times Aleph? What does that mean? Well, it just means that you multiply every coefficient by 5. You get that. And that's obviously still a formal sum of points in U. Okay? So we have a natural scaling operation by integer values. And then it's a module. It's a Z module by the same types of proofs as we did before. Same type of proof that worked for F1 works here as well. Okay, so I'm going to leave that as just an assertion. I'm not going to talk about the proof, but the proof is so similar to the other proof that F1 was a module. This is a Z module that, I'll just leave it to your imagination. It works the same way. Okay, and there's no equivalence relation, so we don't have to worry about that. This is the same as C as the 0 chains. Good, so now I'm going to define an operation called the boundary operator. Okay, it's just called that. That's just a name. Oh, actually, it's called that for a very good reason. You'll see why in a second. But the boundary operator is going to take us from 1 chains to 0 chains. Okay? And it's going to be a very special type of operation. So let me explain how it works. Let's say I choose some specific chain, 1 chain, A. So really, I should be writing that as the equivalence class of A. And maybe I should do that for the time being, just to keep things very careful. So that A is going to be a formal sum over all paths gamma, where we have these integer coefficients in brackets, and then we have each one associated with a certain path gamma. But remember that most of these are zeros. Only a finite number of them are non-zero. And then you take the equivalence class, and that's going to be like a typical chain. Well, the boundary operator is going to act on that chain to produce the same exact combination, same coefficients, except that each gamma, each path, is going to be replaced by its final point plus, let me be very careful, a 1 times its final point plus a -1 times its initial point. So you write down basically the same summation with the same exact coefficients for each path. Like each individual path, gamma, has a certain coefficient associated with it. Now, granted, most of these are zeros, but for the ones that are not 0, you have to be, leave them there. But then you replace the actual gamma by this combination. Now notice what this combination is. This is actually a formal sum of points, because gamma final is a point. Let me call it Q. It's a point in the region U. And then gamma initial is another point in U. Let's call it P. See, P and Q are just that gamma is a path, piecewise smooth path, but it has an initial point and it has a terminal point. And so what I'm having here is like a formal sum of points. It's 1 times the point p plus negative 1 times the point q. Notice that the, oh, I'm sorry, it's the other way around. It's 1 times q plus negative 1 times p. So notice that the terminal point is counted positively with a plus 1 coefficient, and then the initial point is counted negatively with a minus 1 coefficient. By convention, just by definition. And the reason for that is because we want the coefficients to reflect the sense of directionality. The path gamma has an orientation. The original path, right, it is a parameterization. And as time increases through its domain, gamma of t will, trace along that curve in a particular direction. We want the coefficients to reflect that sense of directionality. So since we're flowing to the point q, we call that plus 1. And since we're flowing away from the point p, we call that coefficient minus 1. Okay, and then you see we still have to distribute. You still have to take this coefficient and just distribute it to both terms. Okay, so this bracket here really shouldn't be there, because this is just ordinary distribution of an integer. We have some integer coefficient here, which is being distributed over some formal sum of points. So you just have to erase those brackets. And then you see what the answer is. The answer is, it's going to be the sum over all paths gamma of a of gamma times a 1 times a plus 1 times gamma final, and then minus a of gamma, because it was a of gamma times a negative 1 times gamma initial. And that is, again, a formal sum of points. So this is when the original formal sum A had these coefficients. And this defines the value of the boundary operator there. Okay. So the first thing I want to establish about this boundary operator is that it's a linear operator in the module sense. This is a linear operator in the sense of modules. Okay, and what I mean by that, that's a very fancy thing to say, but it means a particularly simple thing. It just means that if I take, let's say, m times a certain chain plus k times another chain, and I take the boundary of that combination, it's the same as just taking m times the boundary of this chain plus k times the boundary of this chain. So the boundary operator delta, or this d, this stylized d, kind of like distributes over plus signs, and then integer coefficients come out. That's what linearity means, in general. Okay, and you can see it directly from this definition, because if I replace this a here by ma plus kb, and by the way, just as a little aside, m times the class of A plus k times the class of B is simply the class of ma plus kb, because that's the way we defined adding and scaling for classes. So anyway, if I replace A with ma plus kb, that's just going to replace all these coefficients with ma of gamma plus kb of gamma. And that's just going to replace these coefficients with those same things. And this minus is going to distribute correctly. Okay, but then as formal sums, like, so let's say if I write down this formal sum where I now have inside here ma of gamma plus kb of gamma, right, times gamma final. And then I have the other term as well, which has minus whatever. Okay, I better write it. So the other term that's in here is going to have like minus m a of gamma minus k b of gamma times gamma initial. Okay, well anyway, you see now, because these are just formal sums of points, the rules of formal sums apply. And we can break this up as like the sum of, or m times the sum of this coefficient times gamma final plus this times gamma initial. And then you'll have k times the sum, same type of thing, but with a b. Okay, in other words, this would be m times the boundary operator acting on that chain plus k times the boundary operator acting on that chain. So yeah, so from this step downward, from this step here and onwards, we're just using rules of formal sums. Formal sums of points. That's what these are. These are formal sums of points. And the rules of formal sums of points just apply, and we can manipulate the expressions. Okay, so that shows that this is a correct statement here. Okay, so we have this boundary operator that takes us from 1 chains to 0 chains in a linear fashion. And notice that there's a relationship to the geometry of paths. The way this boundary operator is constructed builds in the concept of an orientation, a direction of movement along a particular path. Okay. So yeah, remember that if I have a particular path, like it has a reversal, and then there's a certain formal sum corresponding to that path, which is where you just assign it a 1, and everything else gets assigned to 0. And then there's a certain formal sum assigned to that path. And then you have like a chain, which is an equivalence class of that, and then another chain. Now, if I take the boundary of this chain, and I take the boundary of that other chain, these two should be mutual negatives of each other, because after all, the paths are reversals. So let me just draw you a picture. If the original path looks like this, and it runs from P to Q, then this boundary operator here is going to be like 1 times Q plus negative 1 times P. Okay, I don't have enough room to write it. One times Q plus minus 1 times P. Okay, and then the other one, since the reversal has like the same two endpoints but in the reverse order, is going to be, 1 times P plus negative 1 times Q. And notice that those are indeed negatives of each other, because you can factor out a minus 1 from this and write it as minus 1Q plus negative 1P. So yeah, the boundary operators, that's another like relationship geometrically, is that if you represent a path and its reversal as formal sums, or as chains really, and you take the boundary operator of those two chains, they will give like mutual negative answers. Okay, which also means that if I concatenate gamma with its own reversal, let's concatenate, right? So that also has a chain corresponding to it. Let me just erase this to give myself some room. Gamma concatenated with gamma reversal just starts at P, travels to Q, and then travels back along the same points, back to P again. So it's a loop. It's actually a loop. But you see, it has a formal sum associated with it. And then you can take its equivalence class. And in that equivalence class is also this expression. Right? Because we know that concatenation can be broken up as a sum, like under equivalence. So instead of writing it as a concatenation, I can just write it as a sum. But also the reversal can be gotten rid of in favor of a negative inside the brackets. Okay, so what is that? Well, these two terms can be combined because they're like terms. What you end up getting is like 0 times gamma. But that's just the 0 map, because it assigns gamma the value 0, and it automatically assigns everything else the value 0 too. Since anything omitted, and any path that's omitted from the expression is automatically assigned to 0. So if gamma is assigned to 0, and everything else is assigned to 0, then that's just the 0 formal sum. And this gives you the 0 chain. Like, this is like the 0 element of the set of chains. So you see, that's quite interesting, that as a chain, this followed by this, like retracing the same steps, is actually just equivalent to the 0 chain. It is the 0 chain. And its boundary will be 0 as well. And you can see that in two different ways. First of all, you can apply the boundary operator directly to 0, and since it's a linear map, it will give you 0. And that follows from linearity, because you can always regard the 0 map as like 0 times anything. 0 times anything. And then when you take the boundary operator of this, basically by linearity, that 0 coefficient comes out. And then you just end up getting 0 anyway. Okay, so yeah, another way to see this is that by the linearity, you can distribute the boundary operator. And what you'll get is like 1 times Q plus negative 1 times P, okay, plus 1 times P plus negative 1 times Q. When you add those two, in other words. Because that's what this sum is here. And since the boundary operator is linear, taking the boundary of this whole thing is equivalent to just distributing it. But then you see that all the terms cancel out. You have like a 1 times Q and a minus 1 times Q. They cancel. You also have a 1 times P and a minus 1 times P, which cancel out also. So you see that, and this is actually a more general phenomenon. If you have any loop, its boundary is 0. So that's why the boundary operator is important, or one of the reasons it's important is because it helps us to formally identify the loops as chains. Like, what makes a loop special as a chain is that its boundary is 0. Okay? So, but we also have to understand that there are other chains that also have a boundary of 0 that are not loops. Okay? What I mean by that is something like this. Okay, I'm out of slides here. I don't have any more slides that I can use, so I'm just going to kind of squeeze this into a little corner here. Let's say I have a loop, gamma 1, and then another loop, gamma 2. And I form this combination, let's say 2 gamma 1 plus negative 3 gamma 2. Then I take the equivalence class of that. So that's a chain. That chain is not a loop. Actually, chains are never loops, because loops are paths. Chains are like equivalence classes of formal sums. But the point is this, it doesn't correspond to a single loop. There are two loops here. And we're just forming some combination of them. But this also has a boundary of 0. Because you see, if I take the boundary operator of this, if I hit this with the boundary operator, then by linearity, the boundary operator distributes, right? And then you'll get like 2 times the boundary, or actually just a scalar 2. Don't have to write it in brackets anymore. Times the boundary of gamma 1, which is a formal sum. And then negative 3 times the boundary of gamma 2. But since gamma 1 is a loop, the boundary of gamma 1 will be 0. That is the 0 formal sum of points. That is going to be the 0 formal sum of points. And since gamma 2 is a loop, its boundary is also going to be the 0 formal sum of points. And then you see that 2 times the 0 element plus negative 3 times the 0 element is still the 0 element. So this boundary is still 0, even though this chain is not a loop, or it doesn't correspond to a single loop. It really corresponds to a kind of collection of loops. Okay, that type of thing is going to be called a cycle. That's what a cycle is. It's basically a formal sum of loops. You take a finite number of loops and you form any formal sum of those, and then take its equivalence class. That's going to be called a cycle. Okay, and the cycles are denoted as like a z1, so cycles in U. The set of all cycles in U is denoted as a z. Okay, that's because in German the word cycle is like a cycle, something like that. I don't know how to spell it, but maybe something like that. Maybe something like that, I don't know. But anyway, yeah, in German the word cycle starts with a z, so that's where this letter z comes from. Okay, so the cycles are just special chains. So like the set of cycles, 1 cycles, is inside the set of 1 chains. I probably should write that as a kind of script z to be in keeping. I don't really know how to write a script z, but to be in keeping with our general style of notation, I'm using script letters. But anyway, yeah, the set of 1 cycles, script z of 1 of U is a subset of the set of 1 chains. But it's just the ones that have a boundary of 0. So it's exactly those chains that have a boundary equal to 0. And we can identify those formally as essentially formal sums of loops. Okay? So since I'm out of slides, I'm going to end this video here, and I'll continue on with this topic in the next video. But basically, what we'll start with in the next video is we want to sort of characterize the cycles in a number of different ways, a number of equivalent ways. One way to characterize a cycle is that it's just any chain whose boundary is 0. Another way to characterize the cycle is that it's a formal sum of loops. Another way to characterize it is that if you take all the paths involved in it and you look at all of its initial points, all the initial points of those paths can be paired up with terminal points in such a way that each initial point is also a terminal point the same exact number of times. See, like gamma 1 has an initial point, which is also its terminal point. And then gamma 2 has an initial point, which is also its terminal point. So if I just look at the set of initial points, let me call this point like P and this one Q. If I look at the set of initial points and look at the set of terminal points, those are the same set. Okay, and so anyway, there are a number of different equivalent ways of characterizing when a chain happens to be a cycle. And that's what we're going to start with in the next video. Now, let me just give you the big reveal. Where is this all going? Why bother with this whole technology of chains and cycles, or this whole machinery, which is extremely elaborate? I'm sure you'll agree that this whole machinery of chains and cycles is very, very elaborate and very far from sort of geometric intuition. But it's really worth it, because what we're going to end up finding is that if, let's say, A is a cycle, okay, I really should write it as the equivalence class of A. If that happens to be a cycle in U, and if U is simply connected, so it has no holes in it, and if F is analytic on the region U, then what we're going to find is that the integral of F on that cycle. Now, you'll remember that I defined integration on a formal sum. So, okay, if A is this formal sum of paths, the way we integrate on A is by just forming the same sum with the same coefficients, but you integrate on all the paths separately. Now, there's only a finite number of paths you have to worry about, because all the other coefficients are 0, so you don't have to calculate these integrals for every single path. You just have to calculate those integrals for the finite number of paths that have non-zero coefficients. Then you just put that same coefficient in front of that integral sign. But we can also define, like, integration on a chain, and it's just the same definition. But now you're going to ask, well, wait a second, what if I have 2 equivalent formal sums? Then their classes should be the same object, which means that these 2 integrals should be the same. But this integral is just the integral over b. So how do I really know that this integral over this formal sum is the same as this integral over that formal sum? Since the 2 formal sums are not the same, they're just equivalent. Hey, that's kind of a great question, but it's obvious what the answer is. All of our equivalence relations, all of our moves, remember that an equivalence relation means that there's a sequence of moves. All of those moves were so constructed, so chosen, so that this equality would be true. Right? For example, representing a concatenation as like a sum was chosen specifically to make this true, that these 2 integrals would come out equal. Right? So the way we chose our rules was exactly so as to make this come out true, that whenever A and B are equivalent formal sums, they give the same integral for F. Like, they give the same integral for any integrand, any continuous integrand on that region. So indeed, it's meaningful to integrate on a chain. Okay, we have integration at the level of a path. So yeah, there are like three types of integration. There's integration at the level of a path, which we understand completely. We've been working with that for many months now. Now there's integration also on a formal sum, which is defined by this formula, in terms of this original. Because at the end of the day, you still have to compute all of these path integrals. So integration on a formal sum is defined in terms of integration on paths. Okay, but then there's still one more level, which is integration on a chain, an equivalence class. And that's also meaningful. It's just the same. It's just the same as this. It's just that to check that it's meaningful, you have to check that if a and b are equivalent formal sums, then the integral on a of any f is the same as the integral of b. And that is indeed a true theorem, just by the way we constructed our equivalence relation. So we therefore, the value of this integral depends not on a itself, but only on the class of a. And so it's meaningful to talk about integration of a function on a chain. Okay, well, anyway, if that chain happens to be a cycle, and if the region is simply connected, it has no holes, and the function is analytic on that region, then we will get 0 for the value of that integral. And that's the Cauchy-Goursat version 5. It's the most far-reaching version of Cauchy-Goursat, because these cycles can be very complicated. You see, the cycles can look like this. Like a cycle can have a loop like this, and then another loop like this, and just be a formal combination of those two. Or maybe it has a loop like this, and then a loop like that, and a loop like that. It's some formal combination of those three. So you see that the objects that we're integrating on are much, much more general than just a single loop. And yet the Cauchy-Goursat equation still comes out true. So this is Cauchy-Goursat version 5, and it's the best, most general version that implies all the other ones, that encompasses, embraces all the other ones. And so that's what we're going to prove next. So yeah, next video we'll start with characterizing cycles in several different equivalent ways, and then we're going to prove this version of the Cauchy-Goursat. Okay, so I'll see you guys in the next video.